Thank you very much. Today I'm just going to give you an overview of some of the work that we have done in Antarctica, and really looking at how we've used drones for remote sensing, for conservation planning in particular. Just see if this changes slides. Give me 1 second. For some reason just a second, please.
We can see your second slide now.
You can? Oh,
yes.
Good. Okay. It just wasn't changing slides. All right. I'll go back to that's the third slide. Sorry, I'll start from the beginning again. The second slide is basically showing you the sort of work that we have done. Oh dear, it doesn't see. Oh, there we go. So since 2014, we have developed and we have implemented UAS or drone-based methods for high spatial and high spectral resolution mapping of these coastal and terrestrial habitats in several key priority Antarctic conservation areas, or ASPAs, Antarctic Specially Protected Areas. We have also conducted UAS surveys of Scott Base, which is the New Zealand base, for their redevelopment planning. And we've had some wonderful and exciting sort of spin-outs from the work that we've done, and Mel, who was the first speaker, has been involved in, and that was the LiDAR and photogrammetry surveys we did for virtual reality of one of the historic huts. UAVs are a fantastic tool to use in Antarctica. They offer this ability to undertake a rapid survey that is low impact, that you can do without actually physically entering the ASPA. They are highly precise and accurate. They're repeatable. You can follow your waypoint navigation, and it's affordable. The surveys that we've done have then provided quantifiable data on human impacts, as well as looking at changes in natural variability and changes that may be related to climate change. But we've had some challenges that we've had to overcome, and these challenges have varied. For example, one challenge that you consider, we're often asked, why can't you do these surveys from manned helicopters? Because the New Zealand base and the American base have a lot of helicopters flying all around the valleys, doing all sorts of work and dropping scientists off. One of the problems is because the technical sensors that we use on board the drones require precision flight lines for surveying. For example, if we have a 25-meter transect line, we have to have spacing around 60% overlap, and we fly at about 100 meters. I certainly would not want to do that in a manned helicopter, and it would be very, very challenging indeed. You cannot use manned helicopters and manned aircraft to gain that kind of precision. The other challenge that we face is that magnetic compasses don't work properly at high latitudes. Those off-the-shelf drones that you purchase are not guaranteed for use in polar latitudes. And that's a big issue. You can't just apply a declination correction. It's just simply not enough. Why is that a problem? Because multi-rotor drones all rely heavily on compasses to fly, particularly when you're flying for photogrammetry or structure from motion, and you need to use that automated waypoint navigation. Other challenges that we hadn't really thought about were things like snow cover. When it snows, you simply can't see through the snow. These are the sorts of days in Antarctica when you decide to watch a movie or do something else. The other challenges, things like frostbite, using this high-tech equipment, freezing levels of the equipment and how that will affect them, getting heaters for sensors and so forth. I'm just going to give you a few examples of some of the work that we have done, starting with Scott Base, the New Zealand base. It's located here on Ross Island, and it's very close to the dry valleys. So a lot of the Antarctic New Zealand work is usually around dry valley research or around the Ross Island itself. We're next door, as I said, to the American base, so we travel by aircraft, and if you look in the far distance, you can see this big ice sheet. Some of it's sea ice, and then there's a line across the sea ice, and beyond that is the permanent ice sheet. And on that permanent ice sheet, just in the distance of this image, you can see where the airfield is. We get flown into Antarctica and we fly back. We don't go by ship. What we do while we're down there, again, as I said, we collect imagery. We often plan our workflow prior to departing New Zealand. We'll spend a lot of time looking at our flight plans, deciding what we're going to do, looking at the area that needs to be covered, the scale of the question, and trying to figure out what's the optimal overlap when we're carrying multiple sensors on a UAV, and what is the optimal UAV design, and so forth. We then go to Antarctica, do the drone flights or the UAS flights. At the same time, we conduct ground control point measurements and vegetation surveys. That's basically what we do in Antarctica, those two steps. We then take the data back, usually to New Zealand or wherever we're going, and we do post-processing, final map production, and other outputs. And we were very lucky the last season that we went down there to have Melinda Waterman with us to work on the moss samples and help us with that ground truthing. What are we doing during our vegetation surveys? Well, we've worked very closely with Mel and with Sharon to come up with some very structured sample protocols for ground surveys. We've identified a species, tried to do it in the field, but also in the lab. We've collected, because it's remote sensing in essence, we're collecting hyperspectral reflectance and building our spectral library of Antarctic mosses and lichens and cyanobacteria. We fly with multispectral and sometimes hyperspectral and RGB sensors on board the drones. We embed markers in our imagery, and you can see an example of one of the markers that Mel brought with us, and that's to assist us with classification. And the ground control points that we survey are there really to improve the model accuracy, and we've got systems around how to improve that model accuracy. This is an example of Scott base. This product has sub-centimeter resolution, and if I click on the slide, you'll see just any point on the slide is, has an image associated with it, and it shows you the carving that you can see in front of the Scott base viewing window, and the carving is looking up to the sky. And it's a great example of the types of resolution and the imagery that we produce. So this is what we generate. This is a point cloud, and it's a highly accurate point cloud. It has sub-centimeter resolution. I'll move to what it's used for. Why did we collect this data? Because New Zealand is developing a new base, and these are some plans for the new base. And our products were involved in looking at the cut and fill and the calculations for how much soil would need to be removed to plan for that new base. And that was an engineering application for the sort of work that we are doing. Some of the more exciting work from the vegetation side of things has been at Botany Bay ASPA 154, and that's where we went again with Melinda. And there we were basically mapping an ASPA that's about 500 hectares in size, and collecting information on the vegetation that was present at that site. The management plan that exists for these Antarctic specially protected areas, many of them in existence. The management plans are often involve maps so that you know what you can do where. And also our maps of vegetation. This was the management plan map, and this was the primary data set that we had going into this ASPA. It gave us some contour lines at 50 meters, but it didn't explain to us how steep that site was in the first 50 meters and how it rose from 0 to 50 in a very short space. It had very coarse outlines and delineation of where vegetation was, and much of that vegetation estimate from that time was incorrect. One of the things that we discovered is that there was a team of people there for 6 weeks to do this map, to create this map of vegetation and contours. We were able to assess that site and fly it with drones in under 3 days. Now the scale is hard to understand here because it was, about 3 kilometers along the beachfront, but I'll show you another map this is what we were looking for, and this is why it was essential to have Mel with us. We were looking for lichens, but primarily for moss. This area is one of the southernmost sites for very productive moss beds. And if you look closely in this image in the center, you can see one of Mel's orange markers that was there for us to tie into the drone imagery. It was quite entertaining because you might not be able to see that, but there is actually a rock holding that marker down because the skuas were so excited by the orange markers that they kept plucking them off. And I think it was a constant issue for Melinda. This is our team, Mel, Len Gilman, and we always, because it's a tricky site, it's glacial moraine, the rocks are constantly moving. We had a guide with us from Antarctica, New Zealand, just for safety reasons. This is considered the topmost end of the dry valleys. And this is Ash Redoshi, who was flying the drone. And this is us flying multiple multi-rotor surveys across this landscape. And as I said, it was 500 hectares in size. This is an example product. One end of the beach to the other end of the beach is about 3 kilometers. So it's very hard to sort of zoom in and show you the scale, but these rocks that look like pebbles of sand, you know, are boulders that are much taller than a building. I'm just going to show you a video and I hope it works. This is a video of the point cloud. Oops, sorry, I'll go back. The point cloud that was generated. Now this point cloud is a 3D model of that landscape, and it gives you an idea of the scale and the resolution of the data that we're collecting. Each point has a value of you know, height and X, Y, and Z, but it also has a vegetation value when we take the vegetation to it. One of the things that we discovered by accident in showing these sorts of models to our friends in art and design was that we could create virtual reality experiences out of these models. And that's something that we've had a lot of fun doing. But going back, here is the vegetation, and those areas in red we've classified to determine that they're really those hotspots where the mosses are found. So the yellow and red were areas we delineated as moss. It was then compared to the ground truth data that Mel did with us. So then we could create maps. This is the current map that's in the current management plan for ASPA 154. And these maps are based on the actual drone surveys that we conducted over this site, and also on with validation from the ground truth data that Mel collected. As I said, some other spinouts have happened when we were down in Antarctica and discovered the usefulness of point clouds and what we could do with them. We did one survey in 2018 where we, or I'm sorry, 2016, where we flew over Scott's Hut in Cape Evans, and we did some very, very high resolution fly-throughs of this hut. From that, we've now moved on to doing a project with Hillary's Hut, and we did that in partnership with the Antarctica Heritage Trust, and just completed it. And we had a very short window of opportunity when we were not in lockdown that we launched this product with the New Zealand Prime Minister, and that was on the 31st of July. So you see, we have an amazing interior. This was a great partnership between a designer and ourselves with the drone team and with the Antarctic Heritage Trust, with developing this walkthrough experience that you can all experience and download on Steam. And as you can see, there's that little photo. We did actually meet and greet the Prime Minister, and we actually were able to contact people at that time. So just in conclusion, with our team and what we are hoping to bring to this bid and to the SAFE community is we've conducted 200 UAV flights in Antarctica, with collecting over 80,000 photographs or from multiple sensors to conduct systematic multi-rotor surveys using pre-programmed flight plans and creating high fidelity models of the landscape and ecology at sub-centimeter resolution with our range of sensors. Thank you very much. And this is our team.